Okay, this is the tutorial for Titan-1-2M CAM for your programming portion of your project. First step, again, we're going to go to the data panel and you're going to open your -2M model that you created that should reflect the block with the series of 7 holes in it. Now we're going to be proceeding with the same workpiece in the lab portion, so you already have the block machined to size. We're going to move a little bit faster than last time, but you'll be in model mode most likely by default, and you're going to switch to manufacturer mode. The menus across the top stay the same, change, and you should have the setup information here on the left. Make sure you're in inch coordinates or inch units, and you're going to select setups, and you're going to create a new setup. And this time around, your stock is basically the model itself. Because we've machined the outside to size, all the material being removed is from within the boundaries of the actual model. So what you're going to do is go to the stock tab. Instead of adding stock to sides, there's no additional stock added. So your dimension should be 4 inch by 1.9 by 0.75. Okay, so we move back to the setup tab and we need to set our origin. Now there's a glitch with Fusion 360 where if your origin of where you want the part to have is coincident with the coordinate system the model was made, you won't be able to select the box point. And we're going to change this to z-axis plane and x-axis. Again, our z-plane is here, our x-axis is here, and we're going to use a model box point of here, a stock box point of here. Now if it doesn't let you select it, the reason is you drew your model with your origin already there. So if it doesn't allow you to select it like these other locations, you have to change this to model origin, and it will locate it where that origin was. So you may run into that issue. Okay. Now we're going to go to the last page, and you're going to set the post processor for this to be program 1003, and this is going to be operation 3, and with a work coordinate system of 1, and you're going to select OK. So your axis orientation should be X pointing to the right, which is positive, Y pointing this way, positive and Y, and Z pointing at the orientation of the spindle of the machine. Okay, so this program is going to consist of 3 operations, and they're all forms of drilling operations. The first operation is going to be a spot drill. What we're going to do is go in with a cone-shaped cutter that's going to spot drill the center of each of these holes, and it's going to go down deep enough to make the countersink. What that does is allow the drill that follows to center on that feature and help it guide and go in straight. The third operation after the drill is going to be the tap that forms the threads. We're going to go to drilling, drill, And then we're going to select from the Titan library our 1/4 inch chamfer mill. So in the shown image, there's a image of a Kennametal brand carbide chamfer mill, similar to what you'd be using in the lab. And as you can see, it looks like somewhat like an end mill where they have a couple flutes, but it has a pointed tip on it. And so it's designed to cut chamfers, which are angles, and our particular application uses a 90-degree included angle chamfer mill, which makes a equal height and width chamfer at 45 degrees as it profiles along. They do have a small amount of side flute, but they're primarily designed just to cut on the angled portion of what you see on the image there. We are going to be using this chamfer mill as another application instead of a spot drill to spot drill the hole locations on this Titan part. Which should be tool 15. We then set the RPM at 4,000. We're going to leave the surface speed alone. Our plunge rate is going to be 12 inches a minute. And then our retract rate will be the same, 12 inches a minute. Slow for a drilling cutter. It has a very sharp tip, and it's easy to overheat and break that tip. Geometry. We're going to select faces, and we're going to select the chamfer itself. And we can select this box that says select same diameter, and it's going to pick up every feature that's like that. And provided we have this okay, and there are some options that show up, like only same Z height, top height. If you had multiple levels and you only wanted to do the drilling at one of those levels, you would select that box, and it's only going to select the holes that are at the same Z level as the one you selected. Okay, we're not using a containment boundary, and auto merge hole segments. We're not going to worry about that in this example. And we don't have varying depths, so if we had different depths, you could order them so that all the drilling at the same before moving on to the next zone. We do want to optimize order, and so that it takes the shortest path between each of the holes. Okay, and order inside out or reverse order, we don't really care which one it starts with, and we're not doing a circular pattern, so it wouldn't be starting at, say, the inside of a spiral and working its way out, or vice versa. It doesn't matter for our application. The tool orientation, again, is only using 4th and 5th axis. So we'll move on to heights, and we're going to set our retracts heights. So because our stock is our model, the retract height being set to either is semantics. So so our clearance height set at the retract, we're going to leave that at default. Our feed height is going to be starting at the top height plus 0.2 of the, and the top height is being set as the top of the holes we selected, which are those. Okay. Our bottom height, in this case, we are going to also base off the whole top, because we want to control the depth of the chamfer. But we're going to offset from that top a depth that's going to produce the chamfer diameter of 0.205. So we need to go to a depth of half of that because it's a 90-degree chamfer mill tip. So we're going to put it in a negative 0.1025. Okay, and we're going to move on to the next tab, which is cycle. So we are going to use a counterboring cycle. Some descriptions is countersinking or spot drilling, but in this software it's calling it a counterbore, and it's the actual type of cycle that's output from the machine. So this cycle goes down to the depth and then gives us the option in one shot, gives us an option to dwell, which means it's going to pause for 1 second at the bottom of the hole to make sure that the finish is good and that chamfer mill is really seek the center of its rotation. And then it'll retract. So it just does one plunge down and then pulls back up. Okay, so we've set all those parameters and we're going to hit OK. And now we have our, if we zoom in, we can see that our chamfer mill should be milling pretty close to that surface we have modeled there. Okay, so that's our first routine. It shows up here with tool 15. Our next operation is going to be drilling with a tap drill. And it's a specific size drill that goes along with the size thread we're using. So we're going to go to drilling, and we're going to drill, and we need to select the tap drill from the Titan library for the 1032 tap, which should be this tool number 10. So this image shows a standard drill bit. Now, drill bit technology has changed a lot over the years, and there's a lot of high performance drills, varying helix, which is a spiral you see there, and different tip geometry. A standard jobber length drill, which is your standard drill you'd buy at the hardware store, has a 118 degree included angle tip, and that's what we're using for this course. But a lot of the newer technologies have different angle tips, so you really have to look at the specifications for the tooling when you're going to purchase it. 30 degrees has become, or 130 degrees has become pretty common, and also different coatings. So the one in the image there has what's called a tin coating on it, which is thin coating of titanium to help cover the surface so that material doesn't stick to the drill. And that's very specific to the particular material you're going to be cutting. The drill you use in the lab may or may not have that coating on it, and for the purposes of this demonstration it's somewhat irrelevant. But you do need to account for that drill tip, because the drawing depth for a hole is to the shoulder, which is the edge where the tip starts, and so you need a full diameter minimum to what the drawing says, plus the tip, unless there's special notes on the drawing. I double click on tool 10. We're also going to go 4,000 RPM. We're going to go a little slower. We're going to go 10 inches a minute with a retract of 10 inches a minute. And then we're going to move on to the geometry tab. We're going to select faces. I'm going to select this one. And then I'm going to select same diameter, and it'll populate in all the locations that have that same diameter. We're not going to worry about these other parameters again because that have popped up, and all of these rest are going to stay at default provided we have optimize order selected. We're now going to move on to heights, and we're going to leave the first few at default because our stock is the same size as our model. It's semantics whether this is at stock top or model top. Our feed height is going to go from the top height, And we want to select model top here. It's going to default to hole top, but because we have the chamfer, we want to make sure that our drill bit is starting its peck before it's below the bottom of the chamfer. It's calculating the top of the hole is what I have highlighted here. We actually want the first Z peck to be at this height. So I've changed this to model top, and our bottom height is going to be the bottom of the hole. And we do want to select this drill tip through bottom, which is going to make the drill tip extend down to be beyond the shoulder. So the whole depth of the hole will be correct with the shoulder diameter going to the model depth and the tip going beyond. That'll give us our clearance for chip packing in the tapping cycle. So then we move on and select cycle. Now we don't want to take all this material off at once in one shot for each hole. These are deeper holes, so we're going to select deep drilling with full retract. And what this is going to do is the drill bit is going to come down by an increment, pull out, go down a little bit farther, pull out, and that pulls the chip out of the hole. For aluminum and softer materials, it's a good thing to clear the chip with each pass. So our peck depth, we're going to set at 0.04. And then our peck depth reduction, we're not going to worry about that. For if it was a super deep hole, you might do that, so that each subsequent peck is shallower, allowing the cutter to right itself in between pass. Minimum peck depth is 0.04, and we're not going to dwell, and we're not going to, so we don't need to put a dwell cycle in. We're going to select OK, and it should have just generated all the tool path, roughly in the same order as the last one. And now we move on to our third drilling cycle, which is going to be our tapping cycle. So we go to drilling, drill. We're going to select a new tool, which is going to be tool 13 from the Titan library, which is our 1032 right hand tap. Okay, this is a graphic, shows a tap. This particular type is a roll tap. There are two major types of taps as far as how they form the thread. In harder materials, you have to use what's called a cut tap, and it actually cuts material, and the hole is drilled the minor diameter of the thread. A roll tap, like what Titan describes in his video and uses in his library, the hole is drilled larger, and the tool actually deforms the metal instead of cutting it. And it actually, in soft materials like stainless steel and aluminum, it actually forms a harder thread because it work hardens, and that you don't have to deal with the chips and burrs if you're dealing with foreign objects of destruction, like in the aircraft industry. They also last a lot longer. It's possible you could be using either one, depending on what your application is. In harder materials, you can't use roll taps. So what's important to really understand, though, is that the tap drill size is different for the two different systems. Now, taps come with different end geometries. Some of them are called bottoming taps, so they only have one lead-in cutting thread, and the standard ones have about 3 or 4. So the different style taps customized. But in a CNC machine, you don't tend to use bottoming taps unless you've gone in with another tap before that one. Okay, so that's the quick rundown on taps, and we'll move on with our programming. Once we've selected that, we can double click or hit OK, and it changes. We're going to change the default RPM to 700, a little bit faster, but you don't want to go too fast with taps, and do not change the surface speed because that is calculated out at the correct speed to make the threads per inch ratio that we need. Okay, we're going to go to geometry, and again I'm going to be in select faces, and we're going to select that hole, and we're going to select same diameter. Now that we've got all of the holes, it picks them all up. Okay, and we're going to go to heights, and again our retract height is going to stay at default. Our clearance height, our retract height is going to stay at default. Our feed height is going to stay at default, and then our top height, again we're going to change it from hole top to model top because we want our tap to start its cycle at the very top of this feature, not the top of the threaded feature. And then our bottom height is not going to be based off the bottom of the overall hole because we want our tap to only go the depth that the drawing calls out, and if we hit the bottom of the hole or get close to it, pack chips in the bottom, we're going to break our tap. So our print dimension says that we should have a threaded hole with 0.38 depth of thread minimum, fully formed. The first three teeth on the tap don't actually cut anything, or they cut progressively and don't form a full thread. So we're going to go about 100 thousandths, or that would be 0.1 deeper, and but that is still shallower than the 0.505 that our tap drill is going. Should leave enough room in the bottom for chip clearance and not break our tap. So after we have all those parameters set, we're going to move on to the cycle tab and select right hand tapping from the menu, and we're going to leave dwelling at 0 seconds. We don't want to dwell. Okay, and it should show our drilling cycle, or our tapping cycle. Now I'm going to pick on the whole setup, and then we're going to simulate what our work is done. Okay, so we have our stock simulated, and we're going to hit go. So we have our spot drill coming around, putting the countersink and pre-drilling each hole. We have our tap drill drilling our cycle down from the top to the bottom of the modeled hole, plus the tip of the drill. Does that in all 7 locations. If you're not wanting to watch a full simulation, you can press this and it'll go on to the next operation. Now we're tapping each one of those holes. Done. Okay, so that concludes the programming portion of this part. You will then need to create a setup sheet by making sure you have the setup selected. And I just realized something. Setup 3. Okay, because that's actually our third setup for an entire part. We're just doing it in segments. Okay, so we're going to highlight setup 3, and we're going to select setup sheet. We're going to save it off in either HTML or PDF. Should look something like this. Shows our origin. You want to have a useful image here. Shows we're going to be checking RPMs and minimum maximum Z's. So once you uploaded this for approval, and you get approval, you'll then go and post-process that code again to the HAWS pre-NGC, new next generation controller. You're going to make sure it says Operation 3, and once you post it, you're going to post it to a location and like your USB memory stick, and that's what you'll transfer it to the machine on. And again, you got to wait for instructor approval. This concludes the tutorial for Titan-1-2M cam, and we'll see you on the next one.